Okay. Let's go back here, full screen. Slideshow. There we go. Right. Right. Relative motion means whether the coil, if you can imagine a coil of wires here, whether I put a magnet in or pull a magnet out, changing the magnetic field that's going in and out of the coil, or I keep this steady and I move the coil over the and off and over and off and everything, it's effectively the same thing, right? From their point of view, right? So that's what I mean by relative motion. It doesn't mean one doesn't have to move into the other, right? Okay, we good? Ready to move on? Yes, Gio is nodding his head. Max is nodding his head. We'll move to the next slide. There's only 9 slides here total. Let me erase the things that I underlined. Okay. An induced EMF or voltage is proportional to the rate of change in B, right? The rate of change in the magnetic field, the area of the loop, and the angle between the two, the rate of change of the magnetic flux. So we're going to use this, introducing this new term called flux. Okay, flux. This is our symbol for flux. Magnetic flux is equal to the magnetic field times the area times the angle of the two. So what does that mean? I'll try and talk it out, and then I have a video. It's a Khan Academy video that can explain it, I think, pretty well. It draws pictures and everything, so it'll explain it better than I can do it. But the idea of magnetic flux is flux in general, let's put it that way, is if you can imagine these magnetic field lines going through, imagine that this is a square, right? The magnetic field lines are going down the screen here. Imagine that this here is a rectangle or a square box or square piece of metal that's going in and out, right? So flux is a measurement of the amount of magnetic field going through the area of the square, right? Times the cosine. So if you can see, as I rotate, first of all, the cosine of 90 degrees, right? They're 90 degrees to each other. Cosine of 90 degrees is 1, right? So after 90 degrees, this kind of drops out of our equation. But if you can imagine my square here, as I rotate it, and that's what we're showing here, as we rotate that square, there's less and less area for the magnetic field lines to go through. So there's less amount of flux going through. And if they're parallel to each other, there's no area for the magnetic field lines to pass through the open square, open loop of that metal, whatever, right? That metal square. So when they're 90 degrees from each other, the cosine of 90 is 0. We have no flux, right? So that's what the idea of flux is. The video shows it a lot better than I do. All right, so let me share the video. So I'm gonna, I think I have to hit share when it's in full screen, right? If I just click on it there, it's in edit mode. So if I go this and then I click on that, it takes me to the link. Now I have to escape it because the link's coming up on, and I have to drag this over here. Okay. Now we're just waiting for the video to load. Come on. Come on. Come on. This is disappointing. This is disappointing. La 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 la. Why isn't it loading? Well, shucks. I was trying to refresh it. Come on, getting closer. There we go. That's what I'm talking about. Okay, I think I'm going to share on the screens. Share screen. Okay, and then hit play. Okay. Well, 10-minute video. Why can't we hear anything? What happened to my volume? Nothing is ever easy in my life. It's muted at the bottom. Thank you. No, where's my cursor? Oh, there it is. All right. Mute. Unmute.
This is, I'm just defining a volume of air.
So we start at the beginning.
What I want to do in this video is give ourselves an introduction or intuition for the term flux in general, and then think about how it applies to the idea of magnetic flux. So first of all, when people are just talking about flux, and this is the easiest way that I know how to conceptualize it, they're talking about how much of something is flowing through a surface in a given amount of time. So if you imagine that this is defining a volume of air right over here, and let's say the air is denser near the bottom of this volume of air, so there's more air down here than there is up here, which is generally true. Air density goes down as you increase altitude. So there's very low density up here. This is in between.
Let's see if I can.
Sense a lot of air down here, and the air is moving. And so let's say that the air is the velocity vectors that I call it. So these are some of the velocity vectors of the air. Let's say the air on this side is moving at, say, a medium velocity. So right over there, but as we move more in that direction, the air is moving faster. So they have larger velocity vectors like that. We see that in general, all of the air is moving in that general direction. That's the way I'm drawing it. I can draw the velocity vectors over here. The air is less dense. The trend in the velocity vector when I go from the left to the right is roughly the same. So that's the flow. Now I'm just sampling some velocity vectors there. So let's talk about flux. And to think about flux, really of any form, you have to think about a surface. So let's imagine you were to put some type of a net. Let's say you were to put a net right over here. And if we were to think about the flux, we would say, well, how much air is traveling through that net in a certain amount of time? We could say how many molecules are traveling in, say, each second. And so this would have some flux associated with relative to the air. But what if we were to take that same net, and we're assuming it's some type of theoretical net that actually does not impede the airflow, but it helps us visualize the surface. What if we were to move that net a little bit to the right, where the density is the same, but the particles are just moving faster? Well, now our flux would increase. So this is larger flux. Larger flux. Why is our flux increased? Because, well, the density is the same, but in any given amount of time, I'm going to have more things going through that surface. Now, what if I were to take that same net and move it up to this high altitude, right over here? That high altitude. Well, the velocity of the molecules are the same, and they're going in the same direction, but there's just fewer of them. So you're going to have fewer molecules traveling through the surface in a given amount of time. So this is going to have smaller flux, and this is all relative to my first one. Smaller flux. Now, what if you were to take the same net, and instead of the air going the direction of the air being perpendicular to the surface, being normal to the surface, what if you were to take the net and reorient it so that the air is going in the same direction of the surface? So what if you were to take the same net and you were to make it like this? So that it's the same net, exactly the same. It's the same net, and you were to make it like this. Well, now how much air is traveling through that net in a given amount of time? Well, now very little to zero air is going to be traveling through that net in a given amount of time. The air is going along the surface, not through the surface. So this one, we could say this one, let's just say that all the air is going exactly in the same direction as the surface, so nothing is going through the surface. We would say that this one has zero flux. Now let's say this net, this theoretical net that actually does not impede the airflow, let's say we can stretch it or contract it. So if we stretch that net in the same, let's say we were to do it, let's say we were to stretch it up like this, so it becomes a bigger net. So it becomes a bigger net like this. Well, now this thing is going to have larger flux because there's just more area. There's more to flow through. So now if you said for this surface, you're going to have a larger flux because there's just going to be more air is going to go through that in a given time. So as you can see, when we think about how much of something is flux in the traditional sense, how much of something goes through a surface in a given unit of time, it depends on in this case, the density of the substance. It depends on its velocity, both the magnitude of the velocity and the direction of the velocity. We see if we orient the surface or if we oriented the velocity so it's not going normal to the surface, perpendicular to the surface, well then we can have our flux go down. And you could have things in between. You could have a net, let's say we took that same original net, but the direction of the air is neither normal nor exactly in the same direction of the surface. Well, this flux is going to be in between that original flux and this one right over here. There is going to be air flowing through. There is going to be air flowing through the actual surface, but it's not going exactly normal to the surface. And as we will explore later, when we get a little bit more mathy into it, we actually care about the component of the vector of the air that is exactly normal when we eventually calculate flux. But this flux is going to be someplace in between this one and the zero flux because the air is going exactly perpendicular. Well, that's just the general, the more basic, or for me, the more intuitive notion of flux. But what do we mean by magnetic flux? Well, like regular flux, we're still dealing with how things are kind of, you could say, going through a surface, but instead of thinking about air particles or water molecules or things like that, we're going to be thinking about a magnetic field. So let me draw a surface. So I have a little bar magnet. This is the north side, this is the south side. We see our field lines, and then I've drawn a couple of the magnetic field vectors in white there. And let's say that we have a surface. We have a surface like this. And so for this surface, when we think about the flux, we want to care about how much, things are actually moving. When we think about magnetic flux, we aren't actually thinking about actual physical things moving through this surface the way we did when we thought about, I guess you could say, traditional or more flow-based flux. But it's a similar idea. We care about the component of the magnetic field and the density of the magnetic field that is normal to this surface. So let's say that this has a given flux. So let's call that, and the notation is phi. Let's say that's the flux of the magnetic field. And once again, it's based on the strength of the magnetic field, and especially the component of the magnetic field vectors that are perpendicular to this actual surface. So this would have one magnetic flux. But if I were to take the same surface and make it parallel to the magnetic field vectors instead of being normal, or now the magnetic field vectors are parallel to it instead of being normal. So now our flux is zero. So this would have zero, or pretty close to zero, so approximately zero magnetic flux. Lux. Now, if I were to take this surface, and instead of orienting this way, I just moved it further away. So instead of putting here, I were to take it all the way out here where the magnetic field is weaker. magnetic field is weaker, so we have a weaker magnetic field out here, the flux would also be. So it has a lot of the same properties as this more physical flux that we were talking about before. But instead of talking about, say, the velocity of the air molecules, we're talking of the velocity vectors of the air molecules and how those relate to the surface. Here we're talking about the magnetic field vectors and how those relate to the surface. But the metaphor, the analogy is still the same. If they are perpendicular, you have larger flux. If they are going in the same direction, you might have zero or very little. You might have very little flux. If you have a weak magnetic field out here, the flux is going to be lower than if you have a strong magnetic field. That's analogous to when you had high density and high velocity, that was a lot of flux, versus low density or low velocity, that is lower flux. And also, we could increase the total surface. So if we stretched that surface, or we had a larger surface right over here, the flux through this surface is going to be larger than the flux through this surface. Let's say this surface is analogous to a surface like this right over here. Let's say that the magnetic field is symmetric on both sides. So the flux through this surface and this surface would be the same. So if you were to stretch it out to be a larger surface, well, now you just have more. You have more of the magnetic field that is now normal to the surface. So hopefully this gives you at least a beginning idea of the notion of magnetic flux and how it relates to more physical flux.
Okay. All right. So like I said, I think that explained it a little bit better, a lot better actually, than the way I said it. But right, again, our formula though, again, right, he talked about the magnetic field, he talked about the area, and then he also kind of implied here, right, he talked a little bit about if it's somewhere in between perpendicular and parallel, right? If this is max and this is zero, then that's got to be something in between max and zero, right? Okay, so let's continue. The induced EMF in a loop of wire is the rate of change in the flux. So, right, the induced EMF, the voltage that gets induced, is equal to the number of loops in that area, right, times the change in flux over time, the rate of change in flux. Okay, so like I said before from the very first slide, it's not about the flux, it's about how the flux changes. That's what's inducing an EMF, and that's what's going to induce a current, right? That change in flux. Okay. And I have another video for us to watch, and I think that should take us to the end of the class. All right, that should take us to the end of the class. We're here till 11:57, so that's about 10 minutes from now. Okay, so we'll watch one more video along the way, and then we'll wrap it up for the day. Okay. All right, we good? We have this copied down? Anybody? Yes? Okay. Here we go. This time. Am I sharing this? You guys at home, can you see the video on the screen? Or
Yes,
no?
I can see it.
Okay, beautiful. All right, because I wasn't sure what happens here. Okay. Come on. There we go. So only 5 minutes, this one. Full screen. Unmute. Let's start here. Play.
We talk about how a current is flowing through a wire and induce a magnetic field. So what we're going to talk about in this video go the other way. How a change in a magnetic field can affect or induce a current in a loop of wire. So we're going to be going from a change in, and actually we're going to focus on magnetic flux. Magnetic flux through a loop. Through a loop. And we're going to see how this actually induces a current in them. So it induces a current, induced current. So this right over here, this is my attempt at drawing a magnetic field, and these are the magnetic field lines. They don't look like lines because they're all popping out of the screen. They're moving towards you, towards the viewer. So you can view these as the tips of the arrow. There's different ways of showing magnetic fields. You can show magnetic field lines like this. You can also use vectors. And when you're using field lines, the density of the field line tell you how strong the magnetic field is. So if you go to the right here, they're less dense, so the magnetic field is less strong on the right-hand side over here than they are on the left-hand side, or at least that's what I'm trying to depict. Now, if we did it with vectors, we would have bigger arrows pointing out over here than we would over there. But now let's do a loop of, wire. Draw a loop of wire here. So let's say I have a loop of wire that is, this is my loop of wire. My loop of wire. So if I just throw that loop of wire, and if it's stationary, it's in this magnetic field, and the magnetic field isn't changing, I do have some flux going through the surface defined by this wire. And if you're unfamiliar with the term magnetic flux, I encourage you to watch the video on magnetic flux. But if I just have this wire stationary in the magnetic field, nothing is going to happen. But I will be able to induce a current if I change the magnetic flux going through this surface in some way. So for example, right now the magnetic field is pointing out of the screen. If I were to make it even stronger in the direction pointing out of the screen, so I guess one way to think about it is, if the change in the magnetic field, change in the flux, were to get even stronger in the outward direction, I don't know if there's a way to get even stronger in the outward direction, I'll throw a big arrow there. I guess you could say that these things became even denser in this outward direction. It is actually going to induce a current. And the current that it will induce is going to go in that direction. The current is going to go in that direction. It's going to go in a clockwise direction around this. And that is because that change in the magnetic flux that induces a voltage, electromotive force that causes this current to flow. And there's other ways to change the magnetic flux. If I were to lessen the magnetic field in the outward direction, or another way, the change in the magnetic field were inwards, then the current would go the other direction. But the key here is when I change the flux through this surface defined by this wire, it's going to induce a current. The current isn't going to be there. The thing is, the magnetic field is stationary, and I'm not changing this movement anyway. But as soon as I change the flux in some way, I am going to induce a current. I could also, instead of changing the field, I could actually move my coil. I could move it that way. And if I were to move it that way, the flux going through this surface, or I guess coming out of this surface, will increase. Because if I move this to the left, the magnetic field is denser, it's stronger. So there'll be more flux through this area here. So if you move it that way, you also would have a current. Now, if you moved it the other way, if it was on the left-hand side and you moved it that way, it would also induce a current. But now, since the flux is lessening in the outward direction, the current would go the other way. Now, there's other ways to change it. You can actually change the area of this actual loop. If somehow it's made out of some maybe stretchy wire somehow. If you increased let me draw it this way. If you were somehow able to stretch it so it contains, so the actual area increases. You're able to stretch it out so that the actual area increases, which would cause the flux in the out of the screen direction to increase even more. That also would induce a current. And so this whole idea of a change in magnetic flux inducing a current This is the essence, and we'll go deeper in future videos. This is the essence of Faraday's law. Faraday's law. And we'll quantify this more in future videos, but it's just the notion that if I have a loop of wire and I have a changing magnetic flux through the loop of wire, that is going to induce a current in that wire.
Okay. Okay. So, I'm going to, we got like 2 minutes left, right? So the idea here again is that chain, right, as he said, uh-oh, what happened? What happened? Oh, it automatically went to another, went on to the next video. Okay. Right. He talked about in that video how the induced, it got increased or decreased. The direction of that induced current changed to other directions. That's where we'll talk about what causes the, or how we figure out what direction that induced current is going to be. Within that, we'll do that tomorrow as we continue. All right. I think as long, we'll finish up our slides. We should be able to finish up our slides on this unit tomorrow. And we're going to go. We have a 3-day weekend, and I'm telling you now, I am going to ask you to do a little bit of work on, whoa, I didn't turn the lights on. So, right. So you guys, I just realized you guys at home are just seeing my silhouette. Well, I'm going to ask you to, so we can keep up our pace, to do a little bit of work over our 3-day weekend. All right. But I want to finish up our notes on this unit tomorrow. Okay. All right, guys. See you tomorrow. Have a good day. You guys at home don't get to leave until the, or here in the building, don't get to leave until the bell rings. I know Dylan was going to walk away when I say goodbye. Yes. Yeah, that's the idea. All right. If you, well, it's generally passing through. So, right. So it's, think of it as like a window, right? The window is how much air can flow through the window. So if I close the window and I only have this big, right, there's a smaller amount of flux than the open window, right? So we can change that in 2 different ways, right? So we can do it by, well, 3 different ways. We can open the window and let more air in. The wind could blow harder and put more air through, or we can, see guys, or we can change the angle, right? And that's the 3 things, right? B, A, and cosine of the angle.